To get more info, please contact us, +1 678 648 4277. Visit https://www.matlabassignmentexperts.com. https://www.matlabassignmentexperts.com. Email info@matlabassignmentexperts.com. FJSCRAMBLE. FJ SCRAMBLEDSPEECHOREGINALSPEEC. Thus, a spectrum as shown on the left will be translated to that shown on the right. The decoder will restore the correct frequency relationships. Consider a component A sin omega t. We'll want to translate it to a sin omega A minus omega t. From elementary trigonometry, a sin omega A minus omega t equals a sin at a cos omega t minus cos at a sin omega t equals a sin at a sin omega t plus pi/2 minus a sin at plus pi/2 sin omega t, which leads to the following time domain processing to shift a single frequency component. Problem 1. A mini project, an audio scrambler. Text messaging is out of date. You and I have been communicating by sending voice messages to each other as .wav files. It's not that I am paranoid, but everybody is out to get me. In particular, they have been intercepting all of our voice messages. But we are going to outwit them by using Matlab to scramble our voice messages before sending them, making them unintelligible using a secret encoding scheme, and then we will descrambling the messages when we get them. Your task is to design and implement the speech encoder and decoder. The requirement is that the scrambled message should occupy the same audio bandwidth, approximately 300 to 3000 Hz, as the original message, and the descrambled message should have good fidelity. We will use a frequency domain mirroring scheme, where the frequency components are flipped, so that high frequencies are translated to low frequencies and vice versa. A spectral component with frequency omega-1 will be translated to a new frequency omega A minus omega-1, where omega A is known to the sender and recipient. The resulting waveform is unintelligible until the frequency relationships have been restored. The scheme is shown below. Signal processing continuous and discrete. MATLABassignmentexperts.com. A pi/2 phase shifter is easy to build for a single frequency, such as sin at, but when the input signal, such as a speech signal, contains more than just a single component, each spectral component must be shifted by 90. This requires an all-pass filter with a constant phase shift, which is a difficult design task for a continuous filter. Approximations as active or passive filters are available. The Hilbert Transformer is an all-pass filter with a transfer function, which is exactly what we want. The following shows the scrambler implemented with a Hilbert Transformer. Then J omega equals F J omega A minus omega. MATLABassignmentexperts.com. A. Practical implementations of Hilbert transformers are approximations. For example, suppose an implementation has ripple in its passband so that at a particular frequency omega the transfer function is pi, where delta is a perturbation from the ideal response. Find the output G, T, when the input is F, T equals a sin hot. Have any spurious spectral components been introduced? You can do this with simple trigonometric identities. B. Your task is to design, implement, and test an audio scrambler and descrambler using this encoding technique. You should write a pair of MATLAB functions as follows: y_scramble equals encode, f_audio, fs, fa, y_descramble equals decode, y_scramble, fs, fa. Where f audio is a MATLAB array containing the audio file to be processed, fs is the sampling frequency, hertz, of the data in f audio, and fa is the frequency, hertz, around which the spectrum is reflected. The first function should take encode the file, the second restore the scrambled version to the original. We will supply you with two audio files, .wav, that you can download and use. One is an ordinary audio file, ps8 raw.wav, that is to be scrambled and descrambled. The second is one that we have already scrambled, ps8 scrambled.wav. These may be imported into your Matlab workspace using the waveread function. f_audio, fs in bits, equals waveread, my file. See the Matlab help. You should use the Parks-McClellan design function FIRB to design a Hilbert transformer that covers the frequency span 300 to 3000 Hz. The help on FIRB has an example. Be aware that the quality of you scrambling will be affected by the passband ripple that you allow. MATLABassignmentexperts.com. Don't forget that the FIR Hilbert transformer is a causal linear phase system, and that it must have an odd-length impulse response. You will need to add an equivalent delay filter in the other arm. Design an appropriate FIR impulse response. The audio arrays will be large. Use FFT-FILT to do the actual filtering operations. Let's standardize on a reflection frequency FA equals 3500 Hz. To test your scrambler, load the audio file, then compute and plot its magnitude spectrum. Then scramble the file and plot its magnitude spectrum. Make sure it is what you expect. If there are any spurious components, try to find why they are there and fix them. You should submit the following: A. Listings of your two functions. B. Details of your Hilbert transformer design, including plots of the passband ripple and details of the phase response. C. A summary of your approach, including the compromises you made in any design choices. D. Plots of the magnitude spectra of the audio file in ps8 raw.wav. 2. Your scrambled version of ps8 raw.wav. MATLABassignmentexperts.com. 3. The result of descrambling your scrambled version off ps8 raw.wav. Use FFT-SHIFT on the spectra to make them more readable. E. You should upload 3.wav files to the 2.161 MIT server site in the homework section. 1. Your scrambled version of ps8 scrambled.wav. 2. Your descrambled version of ps8 raw scrambled.wav. 3. The result of scrambling then descrambling ps8 raw.wav. Be sure to name the files so that they are clearly identified as yours. We will be available to help if you run into trouble. Problem 2. An analog integrator has a transfer function hs equals 1/s. Use the bilinear transform to find a. The discrete time transfer function h, z, and b. The difference equation for this form of digital integrator. Plot the frequency response functions of the resulting digital integrator. Problem 3. A continuous bandpass filter is described by the transfer function. Derive a recursive computing formula, difference equation, for 1. A step invariant, 2. A root matching, and c. A bilinear transform digital filter based on this system. Assume delta t equals 0.1 s. Problem 4. A digital filter is to be designed to the following specifications. MATLABassignmentexperts.com.